Welcome to Math with Malia. Today we're doing Savvas enVision Algebra 1, Topic 4, Lesson 1, Solving Systems of Equations by Graphing. After this lesson, you'll be able to use graphs to find approximate solutions to systems of equations. We're going to be doing some graphing by hand, so have some graph paper, and then have a graphing calculator, because I'm also going to show you how to graph linear equations on your graphing calculator. For the explore and reason, we have Juan and Leo meeting and driving their ATVs on this trail. Juan is late, so Leo started without him. And you can see their speeds given. Leo is riding at a speed of 12 miles per hour, and Juan is riding at a speed of 15 miles per hour, and the trail is 40 miles long. Part A, write an equation for Leo's distance from starting point after riding for X hours, and write the equation for Juan's distance if he starts H hours after Leo. All right, so for Leo's equation, y is going to be the distance traveled, and his speed is 12 miles, and x is the number of hours, so that's Leo's equation. That's pretty straightforward. They start at the origin, so they have a y-intercept of 0. For Juan, y is going to be his distance. His speed is different. He's going 15 miles per hour, so his x term is 15x, but we have to incorporate his starting time. He starts h hours after, so we don't know the distance he starts at, technically, but we know that it's going to be calculated by multiplying his speed times the number of hours. So Juan's distance can be represented by this equation. Part B asks us to use two graphs to determine who finishes the trail first after 1 hour. Okay, so I did it on another screen, and you can see how I set up the scale. On the x-axis, this was our time, and I used minutes, with each square representing 20 minutes. So here's our 1 hour mark. And on the y-axis measuring distance, I counted every 5 miles. So yep, including 40, the finish line. And Juan's speed is represented here on the red graph. You can see there's his speed at 12 miles an hour. So I just did 12, and they both start at 0. And that was Leo. And Juan is represented by the blue. And you can see his speed is at 15 miles in 1 hour. So at this rate, who's going to finish or reach the starting line first? Well, we can see that Leo has a higher speed, a steeper slope. He is going to reach the finish line first. He actually reaches it there at 160 minutes, or 2 hours and 40 minutes. And it takes Leo just over 3 hours to reach the finish line, to reach 40 miles. Okay, so we can tell at this rate, in 1 hour, Juan should reach the finish line first. How much of a head start must Leo have to finish the trail at the same time as Juan? So this one's a little tricky. We're going to need to do some algebra. So Leo's speed at 12 miles an hour, he's going to finish the trail, so the distance will be 40 miles. So we need to figure out how long it's going to take Leo to finish the trail to get 40 miles based off of his speed. Okay, so just divide by 12. We're solving for x. So it takes Leo 3 1/3 hours to finish the trail. For Juan, we're going to do the same thing. Well, now we know they're going to finish the same time. So this is the time then that we're going to put in for Juan. Because if he's going to finish at the same time, then Juan, who's going faster, is going to have to finish in this time. So we're going to plug in this time for x into Juan's equation. Because, see, we have two variables, so we don't know how long he has to wait. So he's still going a total of 40 miles. Y is still 40. 15 is his speed times the time that we're using. It's going to be the same time as Leo's. Okay, so we'll plug that in. And then we're going to solve for h from Juan's equation. Okay, and then if we do this math, so I'm going to change this, I'm going to cross simplify. That becomes 5. So we have 40 equals 50 plus 15h. I'm running out of room. I don't know if you can see it on the bottom, so I'm going to move it up here. Okay, so if I subtract 50 from both sides, I'll have negative 10 equals 15h. And then divide both sides by 15. H is going to be, well, negative 2/3, but that's fine. 2/3 of an hour. So that means Leo needs 2/3 of an hour head start, or 40 minutes head start. Example 1. Solve the system of equations by graphing. So here's our system of equations. Remember, a system of equations is just 2 or more equations. And the solution then is where both equations have the same solution. One solution works for both equations. That would be the solution to that system. So our first equation is given here, negative 2x minus 4. And so we can graph that. Our y-intercept is at negative 4. And our slope is negative 2. I don't like that they didn't show the y-intercept for this one. Okay, so they're showing you the graph here. If I continued down, the y-intercept would be at negative 4, and then they just reversed the slope. So they went up 2, left 1, up 2, left 1. Okay, so the blue line is the equation, or the graph for negative 2x minus 4. The red line is the equation for 0.5x plus 6, so there it showed the y-intercept. And the slope is 1/2, so we went up 1, down 1. Okay, so you can see from here, up 1 over 2. So from here, this point, I went up 1 over 2. So there's our slope. And the solution is where those two graphs intersect. Where those two lines intersect, that is the solution, because that point at negative 4, 4 would be a solution, a value of x and y. This value would work for both equations at the same time. So this is where both equations have the same value for x and the same value for y. And we can check. If we plug in those values for x and y, if we plug in negative 4 for x here and plug in 4 for y, if we do the arithmetic and do the math, so negative 4 times negative 2 is positive 8, minus 4 is 4. That does equal 4, so that is a solution. Plug it into the second equation. So plug in negative 4 for x, plug in positive 4 for y. Do the math. Half of negative 4 is negative 2. Negative 2 plus 6 is positive 4. That also works. That is true. So this point, negative 4, 4, is a solution for both equations. So it's the solution for the system. So when we're graphing, we're just looking where the two lines intersect. That point is the solution. Try it number 1. Let's graph these two systems and then find the solution. So I'm going to do part A over here. Our first equation, I'll do in red. Okay. Our y-intercept is at negative 2. So here's our y-intercept. And our slope is 1. So up 1 over 2, up 1 over 2, up 1 over 2. Okay, and I'm going to just connect that through just a little bit. Okay, so here's the equation, or the line, the graph for the first equation. And the second equation I'll do in blue. The y-intercept is negative 7. And the slope is 3. So up 3, 1, 2, 3 over 1. Up 3, 1, 2, 3 over 1. I can see the point where they're both going to be the same. I'll do the slope one more time. 1, 2, 3 over 1. So here's the line for the second equation. And the solution again is where they intersect. So where they are the same is that ordered pair, and we're going to write it as an ordered pair. So that is over 2 and down 1. So 2, negative 1 is our solution for the first one. Okay, let's do part B. We'll do part B over here. Here's our first equation, 2x plus 10, so the y-intercept is at positive 10, and the slope is 2. I can't go up, so I'm going to reverse the slope and go down to left 1. Down to left 1. Okay. Since I ran out of room on my grid. When you're graphing, you want to make sure you use a straight edge and get enough points using your slope so you can have a nice straight line. You want to be as accurate as possible when you're using graphing to find solutions to systems of equations, because you need an accurate read for that ordered pair for the point of intersection. Okay, and the second equation I'll do in blue. The y-intercept is at positive 1. The slope is negative 1/4, so it means I go down 1 and to the right 4. Down 1 to the right 4. Down 1 to the right 4. And I'm going to reverse it. I'm going to go up 1, 2, to the left 4. I can see where the point's going to be the same. Keeps disappearing on me. Arrows on the end. Okay, and our point of intersection is right there. We're going to write the ordered pair. It's over 1, 2, 3, negative 4, up 2. So negative 4 comma positive 2 is our solution. Example 2. What is the solution of each system of equations? And we're going to look through, remember, linear equations can have no solution, or they can have one solution, or they can have infinite solutions. So we're going to look through those different examples. Here are our two equations in our system. Okay, and the first one is in standard form. So if we use our intercepts, remember we're going to use when x equals 0 and when y equals 0 to graph. So if x equals 0, then that is 5y equals 25. So then the y coordinate would be 5. Just going to write it like an ordered pair. And then if x equals 0, let me erase this now. If y equals 0, then I have 15x equals 25. And I have 25 over 15, which is 5 over 3. So there's our intercepts. So 1 2/3. Which is, looks like it's right here. There's 5/3. That's our x-intercept, and our y-intercept is at 5. Okay, and then our second equation, it's already in slope-intercept form, so our y-intercept is at 5. Our slope is negative 3, so we go down 3 and over 1. 1, 2, 3 over 1. Down to 3 over 1. Okay, keep going. And we can see we're actually just plotting the same line. Okay, using graphing, we can see that they're both going to give us the same exact line. So then if it's the same line, then every single point on those lines is a solution, because every single point is a point of intersection for those two equations. So since every point on the line is a point of intersection, there are infinite solutions. Okay, so there are infinite solutions to this system of equations. Example B. Well, the first equation we can easily turn into slope-intercept form and just move the 2x over, so then it becomes positive 2x plus 6. Y-intercept is 6. Slope is 2, so that means I would go up 2 over 1, and I'd reverse it, go down 2, left 1. You can see the graph for the first equation in red right there. Okay, there's the first equation. The second equation, again, we're going to use our intercepts. So when x equals 0, y is 4. So the y-intercept is at 4. And when y equals 0, that goes away. Negative 4x equals 8. So then x would equal negative 2. There's my x-intercept. Connect the dots. And there's our equation, or the graph, for the second equation. Look at those lines. They are parallel. They're not going to ever intersect. So there will never be a point of intersection. There will not be a solution to this system because they are parallel. Okay, try it number 2. graph these systems of equations to see how many solutions, if there are infinite solutions or no solutions. Okay, for part A, we have the first equation already in slope-intercept form. So our y-intercept is at 7, and our slope is 1/2, so we'd go up 1 over 2, up 1 over 2. So here's our first equation. I did it in blue. Second equation is in standard form. I'm going to show you something. I'm going to turn this into slope-intercept form. We did this in topic 2. So I need to move my x term to the opposite side, gets the opposite sign. So I would have negative 4x plus 12, and then divide by the coefficient in front of y. So divide each part by negative 8. That gives me y equals 1/2 x minus 3/2. Okay, what do we notice about these two equations? Looking at their slopes, what do we notice? Remember, the slope is the rate. It's the coefficient in front of x. Y equals mx plus b. So right now, m is the same value for each of these two equations. So if the slope is the same, what did we learn in the previous example? If the slope is the same, are they ever going to intersect? Nope. So they will never intersect. They are parallel. So therefore, 3 dots means therefore, no solution. Okay, they will not intersect. It'll be parallel, and it's going to be about like down here. The y-intercept is about here. Okay, but it's still up 1 over 2. So the slope coming from the y-intercept at negative 1.5, up 1 over 2, up 1 over 1 over 2. We can see if we graph them, we should get parallel lines. All right, part B. The first one is in standard form. They're both not in slope-intercept form, but we can turn them into slope-intercept form. So let's just move the 3x over. So I'm going to do 2y equals negative 3x plus 9. Divide everything by 2. Okay. So our first equation is y equals negative 3/2 x plus 9 over 2. And if we were to graph that, that's 4.5. 1, 2, 3, 4.5 is our y-intercept, and our slope is down 3, right 2. So 1, 2, 3, right 2. Down 3, 1, 2, 3, right 2. Okay, that's enough points. So here's our first line. There's our first line in the system. The second one, we just have to get rid of that coefficient. So we have to get rid of the coefficient by multiplying by the reciprocal. So do that to everything. Everything is multiplied by the reciprocal. So then, I'll do this one in blue. So then I'm going to have y equals negative 3/2 x. I just switched those. I'm distributing the 3/2. And then 3/2 times 3 is going to be positive 9 over 2. Okay, wait a minute. What do you notice? These two, when I put them both in slope-intercept form, they are the same exact line. The slope is the same, so we would know they were parallel. But since the y-intercept is also the same, we know it is the same exact line. So if it's the same exact line, that means there are infinite solutions, because every single point on this line would be a solution. Every single point would be a point of intersection. Example 3, our application problem. We're going to write a system of equations and then answer this question. So Monisha and 5 of her friends, so keep that in mind, we have 6 people going to a concert. And they're trying to decide whether to buy tickets online or at the ticket booth. They have $400 to buy the tickets. For what number of tickets will they be the same? So here's one question. How many tickets can they buy where the price would be the same online or at the door? And then the second question we're going to answer is, which way will it cost less for all 5 to attend? So we're going to do 2 things. So you can see in the graphic, we have our information to give us the equation. So at the door, it's just $67. So how would we write that equation for at the door? Well, just 67 times the cost of tickets. So here's the price at the door. Okay, and then online, it tells us here, it costs $62 per ticket with an $18 service fee. One time, no matter how many tickets you buy. So here's the equation for buying them online. Okay, and now we want to see, when do they cost the same? Well, if Y is the total cost, it's going to be the same. So that means they both equal Y, they both equal the same thing. We can just set them equal to each other. Okay, so if this is also called the break-even point, when your 2 equations in the system equal each other. You're just looking for when they break even. Okay, so just to solve, we subtract 62x from both sides. And we get 5x equals 18, divide by 5, divide by 5. The number of tickets is 3 3/5. The decimal is 3.6. Okay, so you can buy 3.6 tickets and it will cost the same either online or at the door. Okay, so here's our answer to the first question. Which way is cheaper for all 6 people to attend? Well, that's easy. We know x is going to equal 6, so we're just going to plug that into our equation. Okay, so for the first equation, 67 times 6, and we'd evaluate, and it would cost $402 to buy the tickets at the door. Okay, and then plug in 6 for the second equation. So 62 times 6 plus 18. This would cost $390 if you buy online. So it's cheaper to purchase them ahead of time online. They couldn't even buy them at the door, right? They don't have enough money to buy them at the door unless someone can find $2 in their pocket or something. So they have to buy them ahead of time online. So here's where we're going to practice graphing the equations on the graphing calculator. So get your graphing calculator out, and we're going to put these 2 equations into our graphing calculator. So to graph our equations, we're going to go up here to y equals. This is a linear equation. Well, we're going to type in a linear equation. Y equals, type in the first equation. Well, since we said the blue one was the second equation, we're going to do the online purchase. So let's put that in 18 plus 62, and then up here where you see next to the alpha button, you have these variables x, t, theta, and n. Use that for x, for your variable. So that'll give us the online equation in blue, and then the at the door price is just 67 times x. So again, use that alpha button where it says link in blue. Okay, when you're using your y equals feature, you want to make sure your plots are off. So check at the top. Plot 1, plot 2, plot 3 need to be not highlighted, and then we're just going to come over and hit graph. We might need to zoom in. So let's check our window. All right, we need to change our window so that we can zoom in. So to change your window, you're going to hit the window button. It's right next to y equals. And for our x-axis, we can go from -1 to 10, and we can count by 1. So that's what this x scale is. We're counting by ones. Now let's think about our dollar amount. -10 is fine. We can go up to, we know it's going to cost at least $400, so we can say like $500 even. And let's count by $50. We don't have enough to count by $1, so let's change our y scale, our dollar scale, to count by $50. Then, when we're graphing, we're going to hit graph, and we should be able to see those 2 graphs. The point of intersection is where they're going to be the solution, where they are the same price. So we can use this calc feature over here on the button that says trace. So hit second, trace, so we get to calculate, the calculate menu, and we're looking for the intersect, number 5. So it's going to ask you, what's your first curve? Put your cursor on the first curve. Yep, that equation at the top, that's our first curve. Okay, and our second line. Yep, that's our second curve. Hit enter. And it says guess, you can just hit enter. So there's the intersection. The point of intersection, the calculator calculated it for you, is at 3.6 and the dollar amount of 241.2, which that's what we got when we looked at the equations and solved algebraically. We saw that they would be the same price at 3.6 tickets. So there's our intersection. So that point of intersection, that's how you can use your graphing calculator. Again, using y equals, and you type in your equations, and then calc, and then intersect. Okay, you do second trace to get to the calculate menu. So the two lines intersect at that point. Okay, that means it would cost $241.20 to buy 3.6 tickets. And we already calculated how much it would cost at the door and online. Okay, so they need to buy them early since they don't have enough. Try it number 3. 2 of the friends realize they are not able to attend the concert. So now instead of 6 people, we have 4 people. So we're going to buy 4 tickets. Is it still better to buy the tickets in advance? What's the difference in the ticket price? So let's plug it into our equations. So 18 plus 62 times 4. This would cost $266 if they buy them online. And if they purchase them at the door, it's $67 times 4, which would be $268. So again, it's still cheaper to buy online. They'll save $2 if they purchase the tickets online. Example 4. Using the graphing calculators sometimes gives us an approximate solution. And you'll see after this example why it's not always best to use our graphing calculators for the solution to a system of equations. So here, they graphed these 2 equations. So they went into y equals, they typed in the first equation, they typed in the second equation, then they did second trace, and then went to the calc menu, and then hit intersect. And then remember, you say, is this your first curve? Yes. Is this your second curve? Yes. What's your guess? So they got that as a solution. Okay, they got that as a solution. So let's check it. If this is the solution, then if I plug in these values for x and y, then we should get the same answer. They should work for both equations, right? If this is a solution. So let's try it. Let's plug it into the first one. Negative 0.429 equals 2 times 1.286 minus 3, okay, and 2 times 1.286 minus 3, this would be negative 0.428. That is not quite negative 0.429. Okay, so we're off by 1,000th. Let's plug it into the second equation. So my y value, negative 0.429, equals negative 5 times my x value, plus 6. Okay, negative 5 times 1.286 is negative 6.43, plus 6. That is negative 0.43. It is not quite negative 0.429. So again, we're off by a little bit. These are not exact solutions using our graphing calculator. So probably what that means is the calculator rounded to the 1,000th. They didn't give us further decimals. This might have been an irrational number, so we have to round. So what would be a better way, instead of using a graphing calculator and getting an approximate solution, we want an exact solution. Let's solve the equation so that we can get an exact solution. Remember, if they're both equal to y, that means they equal the same value. They're going to equal each other. So we can set the 2 equations equal to each other. So here's the first equation. Here's the second equation. We're just going to solve. Move the 5x over by adding 5x to both sides. And then we moved the negative 3 over by adding 3. So here's our opposite operations. 7x equals 9, x equals 9/7. So the fraction is going to be the most accurate answer. We're not going to have to round. And you can see it would be a repeating decimal. Okay, so again, it is a rational number, but since it repeats, we would have to round, so it's best to just leave it as a fraction. Now we can plug in that solution. So we're going to plug in to either equation, y equals 2 times 9/7 minus 3. Y equals 18 over 7 minus 3. 18 divided by 7 minus 3. Y is negative 4.2857, so it does keep going. If I turn it into a fraction, though, y would equal negative 3/7. So the most accurate solution would be 9/7, comma, negative 3/7. Then we're not rounding any decimals, we're getting the most accurate point of intersection. And if we plugged those values in, we could see that we get the same answer to both equations. So here we plugged in our x value to both equations, and we get the same y value. So this is the best answer because it works for both equations. Try it number 4. What solution do you obtain for the systems of equations by graphing, and what is the exact solution? So let's type these into our graphing calculator using our y equals function. So back at y equals, let's clear these out. Type in our first equation, 5x minus 4. And our second equation is negative 6x plus 14. Hit graph. Okay, we can see I'm going to change my zoom. I'm going to go zoom standard. Okay. We can see our solution. So we're going to go to second trace to get to our calculate. Hit intersect. Our first curve, yep, that's our first equation. Hit enter. Our second equation, yes, that's our second equation. Hit enter. Make a guess. You can move the cursor up or down to where it's about. Enter. And okay, so there's our point of intersection. 1.6363 repeating, and our y value is 4.181, so looks like it's repeating also. They just rounded to the 2. They rounded the 1 up to a 2. So using graphing, our solution was, our x value was 1.6363, and I think that repeated, right? And our y value was 4.1818. That repeated. How would we solve it and get an exact solution? Well, they're both equal to y, so they are equal to each other. So we'll write the two equations equal to each other and solve for x and then solve for y. So I'm going to add the 6x to both sides. That means I have to move the 4 to the opposite side. So I'm going to add 6x to both sides. Then I'll add 4 since I'm moving it to the opposite side. I'll get 11x equals 18. X equals 18 over 11. Okay, that's my x value. Plug that into either equation to find y. So y equals 5 times 18 over 11 minus 4. Okay, this equals 18 times 5 is 90 over 11 minus 4, that's 44 elevenths. 90 minus 44 is 46, so y would equal 46 over 11. So my solution, my exact solution, my x value is 18 elevenths. My y value is 46 over 11. And if we did the math, if we divided 18 by 11, we would get that decimal. If we divided 46 by 11, we would get this decimal. Okay, but the fraction, again, is the most accurate answer. Made it to the concept summary. Remember, systems of equations are more than one equation. The solution is where those lines intersect, and you can do that by graphing. You can graph the two equations and then find the point of intersection. There's either one solution. If they're the same line, there are infinite solutions because it's the same exact line. And here's an example. If you divided everything by 2, you would get negative x plus 9. And if they are parallel, notice they have the same slope, but different y-intercepts. So they would be parallel, they would never intersect, there are no solutions. Make sure to leave any questions you have in the comments and come back for lesson 2.